Hi everyone, this is Mrs. GA, and today we're going to talk about rates of change in the natural world and social sciences. Alright, so I have a quick warm-up for you, so please pause the video and give it a try. Alright, go ahead and check your work here. So you can see that for both of these, I started by finding y prime, and then I set that equal to 0 and solved for x. And then from there, I found y double prime below. So you're going to see today when we're working with rates of change, we are going to be working heavily with the first and second derivative and finding things like zeros of our different functions. So the first part of our lesson is really going to focus on the relationship between position, velocity, and acceleration. So let's say that if the position of an object traveling in a straight line at time t is given by s of t, we would call this the position function. Then we could find the average velocity, which is really just the average rate of change of the object over some time period, let's say in b, by doing s of b minus s of a all over b minus a. Right, really this is just the slope of our secant line. Now if we want to find instantaneous velocity, that's when we need to use the derivative of our position function. So it's going to be s prime of t, which we can describe with a limit definition. So the limit as t approaches a of s of t minus s of a all over t minus a. And again, this gives us the instantaneous velocity, and really this also gives us the slope of the tangent line. All right, so velocity, just to make sure we really understand what it is, velocity is the rate of change of position. So the rate of change of the position of our object. And speed and velocity, it's oftentimes, they're kind of mixed up, but speed is just the absolute value of velocity. So velocity actually has a direction. You could have a positive velocity or a negative velocity. But if you want no direction, so I'll add that in here, then we would call that speed. So speed is simply velocity without direction, so the absolute value of direction. Now, an object is going to be at rest when our velocity is equal to 0, right? Because the rate of change is equal to 0, so it is not moving. And if an object turns around at time t, so maybe it's moving right, and then all of a sudden it turns around and starts moving left, or it's moving up, and then all of a sudden it moves down, then the velocity is also going to be 0 at that instant. Now, I do want to point out, this is not to say that whenever the velocity is 0, that you're changing direction, because it's possible to be moving to the right, you stop moving, but then from there you keep going to the right. So just because the velocity is 0 doesn't necessarily mean you're turning around, but if you turn around at that exact instant, our velocity is 0. So then that brings us to acceleration, which is the rate of change of our velocity. And since it's the rate of change of the velocity, well, rate of change implies the derivative. So it's the derivative of our velocity function. So just to kind of tie these all together, we call our position function s of t, or it's oftentimes denoted with this function, which means our velocity function, which we'll call v of t, since it's the rate of change of position, it's s prime of t. And then our acceleration function, which we can call a of t, well, it's the rate of change of velocity, so it's v prime of t. And since it's the rate of change of velocity, well, velocity is the derivative of position, so it actually makes acceleration the second derivative of our position function. So it goes position to velocity to acceleration. All right, so now we're going to talk about the concept of speeding up or slowing down. So by definition, an object is speeding up if the velocity and the acceleration have the same side, and an object is slowing down if the velocity and the acceleration have opposite signs. So really quick, I just want to make sure we understand something about velocity. I think it's really easy to mix up the concept of positive and negative velocity in terms and generalize that with speed. So just because velocity is negative, if velocity is negative, does not necessarily mean that it's moving slow. So I think it'd be really easy to think, okay, if my velocity is positive, then I'm moving fast. If my velocity is negative, then I'm moving slow. When your velocity is negative, it just means that you're moving in the negative direction. So you're actually moving slowest. You're actually moving slowest when the velocity is closest to zero. So actually, the more positive or the more negative you get, the faster you are going. So just keep that in mind. Same thing with acceleration. Just because your acceleration is negative does not necessarily mean by itself that you are slowing down. It just means that the rate of change of your velocity is negative. So please keep that in mind. Positive does not mean faster than negative when we're working with velocity. So let's go back to this idea of speeding up or slowing down, and let's look at these 4 scenarios. So if we have a car and the velocity is moving in the positive direction and the acceleration is also moving in the positive direction, here we see a scenario where we are speeding up. And the reason is because the velocity and acceleration have the same sign. Now let's look at this one. Here, our velocity is moving in the positive direction, but you can see that our acceleration is moving in the negative direction. So when you have a case like that, we are slowing down. Okay, now let's look at this third case. Here you can see that the velocity and the acceleration are both moving in the negative direction. So again, although it's moving negative, that does not mean that it's going slower. Since the velocity and acceleration actually are moving in the same direction, they have the same signs, here we are actually speeding up. And last, here our velocity is moving in a negative direction, but our acceleration is moving in a positive direction. So although we are accelerating in a positive direction, since it's an opposite side from velocity, we're actually slowing down overall. So remember, when you're thinking about this concept of speeding up or slowing down, we can't just look at velocity or even just acceleration. We have to look at the two together and compare the signs of our two functions at any given time. All right, let's try an example together. So here we have a graph of a position function. It's really important that we understand what type of function our graph represents. So this is a position function of a particle moving along a horizontal coordinate axis. So it's kind of moving from left to right. So we're going to look at a few different things. First, let's look at the scale of our axes. So the x-axis represents how many seconds have gone by, and the y-axis represents how many inches we are in either direction, left or right. So if we're on the positive axis here, we're to the right, I guess, of 0. If we're on the negative axis, we are on the left, because again, this represents a particle moving along a horizontal coordinate axis. So I understand that it's a y-axis here, but what it represents is movement to the right and left. And we are always going to say positive is right and negative is left. All right, let's take a look at part A. First, we're going to try to describe when our particle is moving to the left. So we know that left is a negative direction. So we're going to be looking for times when our position is going more negative. And that's going to happen when our slope is negative. Because here I'm changing from 4 inches to the right, and then I'm 3, and then I'm 2, and then I'm 1 inch, and now I'm 0 inches. So you can see that I'm slowly creeping towards the left side of our horizontal axis. So the interval that would describe this is from 2 to 4 seconds. Now let's talk about when our graph is moving to the right, which is a positive direction. So anytime our slope is positive on our position function, we are going to be moving towards the right, or whatever our positive direction is. And that's happening from 4 to 6 seconds. And then when is our function standing still? Well, it's going to be standing still when the position doesn't change. And you can see that when our position function is horizontal, well, that means that it's staying at that position. At 1 second, at half a second, it's 4 inches away. At 1 second, it's 4 inches away. At 1.5 seconds, it's 4 inches away. So anytime our position function is horizontal, we are going to be standing still. So that's from 0 to 2 seconds, and then from 6 to 7 seconds. All right, now we're going to try to graph the particle's velocity on this axis. So where our y-axis now represents velocity in inches per second. So remember, the velocity function is just the derivative of our position function, which of course is the slope of our function at any given point. So for each interval, we want to determine what our slope is, and that will determine the velocity of our function. So here we can see that our slope is 0. In this region here, we can see that our slope is -4 if you do rise over run. In this region right here, we can see that our slope is just 1. And then in this region here, we can see that our slope is 0. So that's where we're going to graph our different intervals of our on our velocity function. So again, from 0 to 2, our velocity is 0. Notice that on the endpoints here, I'm having an open circle because we actually cannot differentiate. Remember, when our graph is pointy or makes a sharp turn like this, so it's going to be open circles here. And then from 2 to 4, the slope of our line is -4, so that's our velocity. So from 2 to 4, we're at y equals -4. And then from 4 to 6, our slope is 1. So we're going to graph that here. And then from 6 to 7, our slope is 0 again, so our velocity function is 0. So now let's see if we can use this to help us determine when our particle is moving the fastest. So remember, fastest implies the speed. And remember, the speed is the absolute value of the velocity. So we don't want the most positive, we want the largest absolute value. And you could see that the largest absolute value on our velocity function is when y is equal to -4 in this interval. So that's going to be the interval from 2 to 4 seconds. So again, when we're talking about speed, we don't really care if it's positive or negative. Again, it's the absolute value of the velocity, so you're looking for the largest absolute value. All right, let's try another one together. Here, we actually have a graph that shows the velocity of a particle that's moving along a horizontal coordinate axis. So you can see here that our y-axis represents the velocity of the particle in meters per second. And here, since it is moving along a horizontal axis, that implies that when the velocity is positive, it's moving in the positive direction, which is going to be towards the right on a horizontal coordinate axis. And when our velocity is negative, that means that our particle is moving towards the left. Okay, so here we want to know, when does the particle reverse direction? So go from moving from the right to the left or vice versa. So that's going to happen when it changes from positive to negative or from negative to positive. So we want to find, first we can look at the x-intercepts of our velocity function, and then we want to actually make sure that it crosses over, because it's very possible for a function to touch the x-axis and keep going, like turn back around. So we want to actually make sure that it changes from positive to negative or negative to positive. And that happens at 2 distinct times. So that happens when t is equal to 1 and when t is equal to 4. All right, part B asks us to describe when our particle is moving at a constant rate, which means simply a constant speed. So it's going to be a constant rate when our velocity is no longer changing. So that's going to be when the slope of our velocity function is equal to 0. So that's going to happen between 5 and 6 seconds. So now we want to find when is the particle moving at its greatest rate. So remember, the greatest rate is going to occur when the absolute value of our velocity is the greatest, because we want the greatest speed. So we're essentially looking for the time when we are farthest away from our x-axis. Whether it's in the positive or negative direction, it doesn't matter. So I see that at this value, this is the farthest point from our x-axis. Here, this looks like it's about maybe 2.5. This looks like it's closer to -3, or it's a little more negative than this is positive. So this will be when our greatest rate occurs, and that happens, since it's asking when, it's when t is equal to 3. So again, we're looking for really the point in time when our function is the farthest away from our x-axis. Now we're going to try to graph our acceleration function wherever it's defined on the axis here. So remember, acceleration is the derivative of our velocity function. So it's going to represent the slope of our velocity function. So we're going to look at each individual segment and see if we can determine the slope. So from here to here, we can see that it's kind of changing right here. So I'm going to put an extra dot to show that this is a different interval. In this interval right here, our slope is -2, if you look at rise over run. In this little interval, our slope is -1. And if you can look from here to here, so from 3 to 5, we can see that our slope is equal to 5 over 2. Again, if you do the rise over run, and then here, our slope is equal to 0. So we're going to take those slopes, and that will help us graph our acceleration function. So again, from 0 to 2, our slope is -2, so that's going to represent our acceleration. From 2 to 3, our slope is -1. Notice I'm not including those turning or those changes or those pointy parts on our graph because we cannot differentiate at values like that. And then from 3 to 5, our slope is 5/2, so 2.5. And then from 5 to 6, our slope is equal to 0. So now that we have a clear idea of what our velocity and acceleration functions look like, we can talk about when our object is speeding up or slowing down. So for this, we're going to look at our velocity and our acceleration function, and we're going to start by describing where these two functions are positive and negative. So I'm just going to number this, so 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay, so for our velocity function, we can see that it's positive, which means above the x-axis, from 0 to 1, so it's positive here. From 1 to 4, you can see in this entire region, it's going to be negative because it's below the x-axis. So from 1 to 4, it's negative, and then from 5 to 6, or from 4 to 6, the remainder of our function, it is going to be positive. And if it helps, we can say 1, 2, 3, 4, 5, 6. And then let's look at our acceleration function just to determine where it's positive or negative. So actually everywhere from 0 to 3, our acceleration function is negative. And then from 3 to 5, it's above the x-axis, so it's positive. And then actually from 5 to 6, our acceleration is actually 0. So I'll just kind of highlight our number line here. Okay, so remember, if we're looking at where an object is speeding up or slowing down, we're looking for regions where either our signs are opposite, meaning that it's slowing down, or the signs are the same, meaning that it is speeding up. So the first region that I see is between 0 and 1. So you can see here, between 0 and 1, velocity is positive, acceleration is negative. So in this region, it's different signs, which means that it is slowing down. And then you could see here from 1 to 3, velocity and acceleration are both negative. So from 1 to 3, it's actually going to be speeding up. And then from 3 to 4, the signs are opposite. So that means that our object is slowing down. And then from 4 to 5, they are both positive. So since they are the same, that means our object is speeding up. And last, if you look at 5 to 6, well, if our acceleration is 0, acceleration is the rate of change of velocity. So that means that the velocity is not changing. So if our velocity is not changing, it is neither speeding up nor slowing down. So let's say from 5 to 6, it is neither. All right, let's try another one together, except this time instead of a graphical representation of one of our functions, here we have an actual function that represents our position. So here's our position function. And we're going to start by finding the velocity at time t. So we know that velocity is simply the derivative of our position function, so we could just find that pretty quickly using our power rule here. So here's our velocity. And then next they ask us to find our acceleration at time t. So we know that acceleration is simply the derivative of velocity, or the second derivative of position. So if we take the derivative of this function, that's our acceleration function. So 6t minus 18. All right, let's look at part C. So now we're going to find when our particle is at rest. And a particle is at rest when the velocity is equal to 0. So we can take our velocity function and set it equal to 0. So we have 3 times t squared minus 6t plus 5. So 3 times t minus 5 times t minus 1. So our velocity is 0 at 2 different times. T is 1 and 5 seconds. All right, so now we want to find the velocity of the particle when the acceleration of the particle when the velocity is 0. So we're essentially going to plug these t values into our acceleration function. So we're going to find a of 1, which is negative 12, and since it's our velocity, or our acceleration, it's going to be meters per second squared. And then we're also going to find a of 5, so we plug it into our function and we get positive 12 meters per second squared. So just remember that just because the velocity is equal to 0 does not mean that the acceleration is equal to 0. Acceleration is the rate of change of the velocity. So again, the velocity could be, or our particle could be at a standstill at that given moment, but it still could have positive or negative acceleration. All right, now let's look at part E. So here we're going to look at when our particle is moving to the right. So remember, with velocity, we have two directions. We have a positive and a negative direction. And in this case, since it's moving along a horizontal line, right represents positive velocity. So we're wondering when our velocity is greater than 0. So for this, we can just look at our velocity function and we can see over what intervals our function is above or below the x-axis. So we see that our zeros here occur at 1 and 5. And then if you just do a little sign analysis, let's plug in 0. If you plug in 0 to each of these factors, this is positive, this is negative, and this is negative, and that gives us a result of a positive. And pick some number between 1 and 2, or 1 and 5. Let's pick 2. If you plug in 2, this is negative, and this is positive, so that gives us a result in a negative, because a negative times a positive gives us a negative. And then pick any number to the right of 5. Maybe let's pick 6. If you plug in 6, this is positive, the result is positive. So this tells us when our velocity function is positive and negative. And again, since we're wondering when our particle is moving to the right, we're wondering when our velocity is positive. So that's between 0 and 1, and then 5 to infinity seconds. All right, let's look at part F. So here, let's draw a diagram to represent the motion of this particle. So to describe the motion, we really want to know when our graph is moving right, when it's moving left, and when it's changing. So our graph is going to change direction when velocity changes from positive to negative or negative to positive. So our graph is actually changing direction at 2 times, when t is equal to 1 and when t is equal to 5. So there's really 3 critical moments in time that we would like to know the positions of our function. We want to know the starting position, so that'd be s of 0. So you could plug that value into our original function and we get 4. And then we want to know s of 1 because that's when our function is changing directions. So again, you would plug that into our position function and we get 11. And then we also want to know the position of our function when it changes positions the last time at 5 seconds. So s of 5. And if you plug that into our position function, we get negative 21. All right, so let's draw our diagram. So remember these values, our y values here represent the horizontal distance along this axis. So our particle is starting 4 feet to the right. So if here's 0, here's 4, and then it goes to positive 11, and then by 5 seconds it's at negative 21. And remember, we know that it changes direction at this point because we go from positive to negative, and then it changes direction again at this point because we go from negative to positive. So moving to the left to moving to the right. So here's our starting point, at 4, and our particle does this. It turns around, and then our particle goes to the left, and then it turns around again, and then it goes to the right infinitely from there, and it will keep on going to the right. All right, so next we're asked to find the total distance traveled over the first 8 seconds. So for this, we will need to find the position of our particle after 8 seconds. So if we plug this again into our position function, we get 60. So to find the total distance traveled, we want to know the distance from here to here, and then here to here, and then here until 60, and we're going to add those up. So the distance between here to here we can find by doing 11 minus 4. So that's the distance between 0 and 1 second, because at 1 second it's at 11. And then we want to find the distance from here to here. So we can do 11 minus negative 21. And again, that's the distance between 1 and 5 seconds when it's here at negative 21. And then we know it goes from negative 21 to positive 60. So to find that, we could do 60 minus negative 21. And that's from 5 to 8 seconds. So if you find each of these individual distances and add them up, so we get 7 plus 32 plus 81, we get 120, and then this is measured in meters. And I do want to remind you, when we're finding a measurement for distance, it's always going to be positive. So if we did negative 21 minus 11, we would just take the absolute value of that to ensure that all of our distances are positive. Okay, then here we are asked to find something similar, but they're saying the displacement of the particle after 8 seconds. So displacement means how far is it from the starting point to where it is at 8 seconds. So we know, again, at the starting point, our initial position is 4, and our position after 8 seconds is 60. So again, they're not asking for the total distance traveled because it is going back and forth. They just want to know how far is it from their end point to their start point. So we just need to find the difference between those two values, and that's 56 meters. So there's a very subtle difference between the total distance and the displacement. So total distance, you have to find all of the distances in the path, but for displacement, it's just the final destination, the distance between your final and your initial locations or positions. All right, the last thing we're going to look at is over what time intervals our object is speeding up or slowing down. So remember, our object will be speeding up when the sign of velocity and acceleration is the same, and it's slowing down when they're opposites. So we want to compare the signs over different intervals, and those intervals will be determined by their x-intercepts, because those are the locations where our function might cross over from negative to positive or from positive to negative. So if you look at the x-intercepts of our velocity function, those are occurring at 1 and 5. So those are going to be two important intervals. So here's 1, here's 5. And then if you look at our acceleration function, we see that that x-intercept, or the 0, occurs at t equals 3 if you solve for t. So we're also going to look at that interval. So you can see we already did the sign analysis for our velocity function, so I'm going to copy that over. It's positive to the left of 1, it's negative between 1 and 5, and then it's positive to the right of 5. And then for our acceleration function, we could just try plugging in different points here, or we could look at a factored form. A factored form of our acceleration function would be 6 times t minus 3, so we could even just plug it into this portion. So let's plug in 0. If we plug in 0 here, we get a negative. So it's negative to the left of 1. Let's test 2. If you plug in 2 here, our function is still negative. And then we know it's going to cross over at t equals 3. And then if you test any point that's larger than 3, you see that our acceleration function will be positive. So from here, we just need to compare the signs in the different intervals. So in this first interval from 0 to 1, the signs are opposite, so that means that our particle is slowing down. In the next interval from 1 to 3, the signs match, so that actually means that our particle is speeding up. And then from 3 to 5, again, we have opposite signs, so our particle is slowing down again. And 5 to infinity, our signs match, so that means that our particle is speeding up. All right, and that is it for this problem. All right, let's try one more together. So here we are given a position function of a particle that's moving along a horizontal line. So here's our position function right here. So we're going to start by finding the velocity at time t, which is just the derivative of our position function. So we will need to do the chain rule here. The derivative of cosine is negative sine. And then the derivative of pi t is just pi. And so that means that our velocity function is negative pi sine of pi times t. And then we want to find the velocity at 1 second. So we're just going to substitute that into our velocity function. So negative pi times the sine of pi. And hopefully remember that the sine of pi is 0. So this will all equal 0. So it's 0 meters per second. All right, so next let's look at when our particle is at rest. And that means that our velocity is 0. So we're going to set our velocity function equal to 0. And we're going to try to solve for t. So the sine of pi t equals 0. And then from here, if we solve for this angle, which is pi t, we know that sine is equal to 0 at 0 plus every pi moving forward or backwards. So I can describe that by saying plus pi n, where n is any integer. And then here we just need to finish solving for t, so we need to divide both parts by pi. So we get t equals 0 plus n. So this is essentially saying that our particle is at rest at 0 or 1 or 2 or 3 because n represents any integer. So it's essentially any integer value of t. Remembering that t must be greater than or equal to 0. All right, next let's look at when our particle is moving forward over the interval 0 to 2 pi. And when we say moving forward, this implies in the positive direction. So that's going to be whenever our velocity function is greater than 0. So when velocity is positive, that means we're moving in the positive direction. So let's look at our velocity function, which again is right here. And we're going to essentially evaluate the sign of our function over any of our x-intercepts, which we found here. So our x-intercepts would be at 0, 1, 2, 3, 4, 5, and 6. And then just after 6 is where 2 pi is. So we're going to stop there because we only want the times between the interval of 0 and 2 pi. So now that we have our x-intercepts, we just need to evaluate the sign between each interval. So we can do this by plugging in some value between each of those x-intercepts, or we could also just kind of think about a picture of this graph. So we know that a period on this graph is 2 pi over pi, which is just 2. So by 2, that's 1 period of our graph. And we know that the amplitude is pi. And the important thing here is that it has this vertical reflection, which means that our graph actually goes down first instead of up first. So our graph is going to look something like this. So that's 1 period of our graph, and then you could continue that on until you get to the 6, so like this. So you can see that it's going to just keep alternating between going below and above the x-axis, which means that here it's negative, here it's positive, negative to positive, and then negative to positive. And you would get that same result if you just plugged in values in each of those intervals. But again, in this case, just thinking about a picture of the graph might make it a little bit easier and a little bit quicker. So then if we want to describe when the particle is moving forward, we're just going to describe all of the times when our velocity is positive. So that's between 1 and 2, 3 and 4, and 5 and 6 seconds. All right, so next we're going to find the total distance traveled over the first 4 seconds. So I want to remind you, when velocity changes from negative to positive or positive to negative, it is changing direction. So our graph is changing direction. Zoom in. It's changing direction at t equals 1, 2, 3, and 4 at any of those integers, but we only want the total distance over the first 4 seconds. So we want to figure out, well, where's the position of the particle at t equals 0? So we're going to plug that into our position function right here. So the cosine of pi times 0 is just equal to 1. And then we want to know the position at 1 second, when it will then change direction. So we do the cosine of pi times 1, which is -1. Then we want to know the position at 2 seconds, which is the next time it will change directions. So cosine of 2 pi, and that's +1. And then we want the position at 3 seconds. So it's back to -1. And last, the ending position at 4 seconds, which would be +1 again. So to find that total distance, we want the distance between each one. Remember, distance is always going to be positive. So if you're going from +1 to -1, this distance traveled here, that's 2 meters. And then from -1 to +1 is another 2 meters, and then we have another 2 meters, and we have another 2 meters. So if you add all of those up, our particle is traveling 8 meters. And that's just in the first 4 seconds. And then last, we're going to talk about the displacement over the first 4 seconds. So that's just comparing our starting position, which we found to be 1, and our ending position, which is 1. So the displacement over the first 4 seconds is actually 0 meters because it ended up in the same exact place that it started. And there you go. All right, so now we're going to look at another application of our first derivative, and that's with the idea of this concept called marginal cost. So let's say we have a cost function, which is represented by c of x. A cost function just gives us the total cost of producing x units of some item. So we know if the number of items produced changes, let's say from x1 to x2, then of course the cost is going to change, and we can find that change in cost by seeing the cost of producing x2 items and subtract it from the cost of producing x1 items. So that's the change in total cost. But what if we wanted to find the average rate of change in cost? So this is kind of like finding the average velocity of a particle over a given time. We're essentially just going to find the slope of our secant line. So we can find this average rate of change of cost by doing change in y values over change in x values. So again, this is essentially just the slope of the secant line. But then, just like we do with anytime we're discussing a derivative, let's imagine that that change of x, the difference, or delta x, so the difference between those two x values approaches 0. So they get closer and closer together. This would be the instantaneous rate of change of cost, which is known as the marginal cost. So the idea of marginal cost is simply the estimate. It's an estimate for the cost of producing one more unit at any given number of units currently being produced. So again, this is what happens as delta x approaches 0. So we do our limit definition of our derivative essentially. So here's the change in y values over the change in x values, and it's the limit as delta x approaches 0, which is really just, again, the first derivative of our cost function. So the first derivative of our cost function, again, tells us the marginal cost, which would give us a really good estimate of the cost of producing just one more item. So here, really, we're just finding the slope of the tangent line. So same kind of concepts as when we're working with velocity, except now instead of instantaneous rate of change of velocity, now it's the instantaneous rate of change of cost. All right, so let's try one last example together. So here we have the cost of producing X items is given by this cost function listed here. We're going to compute the marginal cost when producing 100 items. So we're essentially saying when we're producing 100 items, how much would it cost to produce just one more item? And then we're going to find the actual cost of producing that extra 101st item. And then we're going to compare the two. So to find that marginal cost, we are going to need to find the derivative of our cost function. So we could do that with just our power rule. And then we'll evaluate that at 100 because that's how many items we're currently producing. So that gives us 4 plus 2, which is 6. So our marginal cost is $6. So that's, again, our estimate for the cost of producing that extra 101st item. And now to find what the actual cost of producing that 101st item is, remember marginal cost is simply an estimate. We can find the cost of producing the 101st item and subtract the cost of producing the 100th item to see what that change is. So if you plug in 101 into our cost function, we'll see that it costs that the total cost is $4,406.02. And if you plug in 100, so the cost to produce 100 items is $4,400 exactly. So if you subtract those two values, that will give us the actual cost of producing that extra value, which would just, or extra item, which would just be $6.02. So again, it's extremely close to what we got for the marginal cost, but it is important to remember that since we're using this derivative, we're kind of using the derivative to estimate a value that's close to 100. So it's kind of like when we did that linearization. So we use the tangent line as an approximation of our actual function. So that's why if you look, the marginal cost is a slight underestimate of what the actual cost is, because it's something like this, where our tangent line is always going to be a little bit less than our original function. All right, so that is all for today's video. Thank you so much for watching.